Hi, my name is Miranda Williams, and this is Lab 5, and I chose to do the falling slinky. The purpose of this lab was to determine the motion of a slinky when it is dropped from static equilibrium. The motion of the slinky was hypothesized to occur in one of three predicted motions. The bottom end falls first, the top end falls first, or both ends fall together. The main physics principle of this lab were Newton's second law, the gravitational force, and the tension force. As you can see here, this is the output of the falling slinky and the data that was collected from the currents. The main ideas, as I stated before, are Newton's second law, the gravitational force, and the tension force. The tension force comes from the slinky and the hand that holds it before it is dropped. And then the gravitational force is, of course, the gravitational force from the earth that acts on the slinky to pull it down. And then Newton's second law includes the position update and the velocity update, and that determined the point at which, and it updated the points of where the slinky occurred. The computational model, so the system was the slinky and the surrounding was Earth's gravitational pull. The are the initial and final these are the initial conditions within my code. The ball position vector, all the values are 0 except for the y position, and the velocity was 0 because the hand was stationary before it dropped the slinky. So here is the real model. We can see that in the picture, when he drops the slinky from his hand, the top of the slinky is collapsing to meet the bottom part of the slinky before the full gravitational force pulls both ends completely down. So whenever the top end is falling, you can see that in the graph how it is straight line, and then whenever the slinky collapses on itself and then continues to fall, that's whenever you have the dips in the graph until the y-axis reaches 0. So this is my computational model. So we had two separate models for the time difference that occurred. So whenever the time was less than 0.76 seconds, of course, we have the velocity update formula and the position update formula, which occurs for Newton's second law. We also have the gravitational force, and we also have the tension force as well. And the F net is going to be the tension force plus the gravitational force. And then while the time was from 0.76 seconds to 3.68 seconds, we still have the same elements. The we still have the gravitational force, and we have the velocity update and the position update as well. And then we also have the force of drag. Here's more of my computational model. So we have the ball mass, which was 0.25, and then our initial conditions that we stated earlier. And then this is what the graph looks like for our computational model. As you can see, it still has that stagnant slope that our real model also had, and that's before the slinky collapses on itself, and that's whenever the top end is moving closer to the bottom end. So for the computation model versus the real model, they both have the same pattern of when the slope is 0 and whenever it dips down. However, the real model contains more deviation than the computational model, and that's the main difference between those two. And both still account for the drag that occurs of the air resistance. So possible sources of error could be the slinky twisting throughout its motion downward, and then the slinky may have been non-uniform. It could have possible variations in the mass distribution or the tension. And then what if I dropped the slinky with a twisting motion? How would the slinky fall? The slinky will still fall top first, however, there would be more of a rotating motion at the bottom of the slinky before the slinky can fully collapse within itself.